Bismillah ar-Rahman ar-Rahim. This is lecture 5 of EE 207, Electromagnetics 1. It's on applications of the Biot-Savart law. So the first example is the magnetic field of the infinite straight wire. Let us consider first a segment of a straight wire between points A and B along the x-axis. The wire carries current in the direction of AZ. It is required to find the magnetic flux density B at a general point near the wire. To simplify the solution, we make use of the symmetry of the problem. The point shown in the figure is any point P on a circle of radius ρ in the xy plane. So the best coordinate system to use is naturally the cylindrical polar coordinate system, ρ, phi, and z. From cylindrical symmetry, phi could assume any value which we choose to be pi over 2. So ρ equals y in this figure, and we can set up the Biot-Savart law for a z-directed current element, IDL equal to I dz prime AZ. So the field coordinate here is R, which is ρ a ρ, and the source point coordinate, the current element position vector, is R prime equal to Z prime AZ. So R minus R prime is ρ a ρ minus Z prime AZ, and the magnitude, which is the distance R, capital R, it is equal to square root of ρ squared plus Z prime squared. So we substitute in the Biot-Savart law. Okay, this is the current element, IDL cross R minus R prime divided 4 pi times the distance cubed. Okay, so carrying out the cross product, the direction of the magnetic field now is along A phi, and A phi is minus AX in this figure, in the X, Y, Z coordinate system. Okay, so now to find the magnetic field, we integrate from ZA to ZB. Okay. To integrate, we use the substitution ρ equal to Z prime tangent alpha, so that dz prime is minus ρ cosecant square alpha d alpha, and the distance cubed becomes ρ cube cosecant cube alpha. Okay, so now the integral simplifies to integration of minus sine alpha d alpha, which is cosine of alpha. So the result is now mu naught I over 4 pi ρ times cosine alpha 2 minus cosine alpha 1. Okay, if the wire is infinite, ZA goes to minus infinity and ZB goes to plus infinity. So alpha 1 would be 180 degrees and alpha 2 would be 0. So B phi would be mu naught I over 2 pi ρ. The cosines combine to a factor of 2. Okay. In general, if the direction of the current is along a unit vector AL, the magnetic field is along the perpendicular to AL and A ρ, and A ρ or ρ represents the perpendicular distance from the point to the wire. Okay. Now we can use this result to calculate the magnetic field of an infinite current sheet. We can imagine a current sheet with current flowing in the x direction. Okay, and we can imagine that the current sheet is made up of strips of current, each of width dy, okay, placed alongside each other and filling up the entire sheet or the entire xy plane. So this is an infinite sheet. Okay, so we need to find the magnetic field, for example, above the sheet. The position vector R of this point is ZAZ, and now we take the position vector of a general current element, which is R prime equal to Y prime times AY. Okay, then IDL here, if we assume that the current density in amperes per meter, okay, to be K, then IDL, which is along X, is K dy prime dx prime AX. Okay. Since integration in the Biot-Savart law is over X and Y, okay, we can integrate over X and use this result. So we will be left with integration over Y. Okay. Okay. So we have a general current strip at Y prime, and this would give us, from the Biot-Savart law, a magnetic field dB1 equal to mu naught K dy prime for the current element in the direction of X cross R minus R prime, so divided by the distance, okay, and this would give us dB1 here, which has two components in the direction of Y and the direction of Z. If we consider the current strip at Y equal to minus Y prime from symmetry of the distribution with respect to the Z-axis, then dB2 would be the same as dB1, but with the direction of Y prime reversed. So if we combine the two, the Z component here cancels, and we multiply by 2 the Y component, so this would be the resultant dB for the two strips, and here the integration would be carried out from 0 to infinity on Y instead of minus infinity to infinity, because we used the two elements. So the integral here can be solved by the substitution Z tangent beta equal to Y prime. Okay, so dy prime is Z secant square beta d beta, and Z square plus Y prime square would be Z square secant square beta, and this cancels, and we will be left with the integration of d beta from 0 to pi over 2, because the angle beta varies from 0 at the origin to pi over 2 at infinity, if you refer to the previous figure. Okay. So what we get is B is minus mu naught K over 2 in the direction of AY for Z greater than 0. Now, if we turn the sheet upside down, rotate 180 degrees, the point above becomes the point below, and its direction reverses. So you will get B mu naught K over 2 in the direction of plus Y. And this is in agreement with the right-hand rule. If we put the thumb in the direction of the current, then the fingers would be in the direction of the magnetic field. So above it would be in the direction of minus Y, and below it would be in the direction of plus Y. Now, if you recall the electric field of the infinite current sheet with charge density rho s, it was rho s over 2 epsilon naught times AZ. You notice the similarity between the two fields, E and B. This is the principle of duality in electromagnetics, where epsilon naught is replaced by 1 over mu naught, and the sheet of the charge density is replaced by the current density in amperes per meter. Okay. But notice the direction that the two are perpendicular to each other. They never come in the same direction.